In this video, we're going to talk about the derivative as a rate of change. So we're going to be talking about things like position, velocity, and acceleration. Now, if you've been watching with my videos, then you know that the derivative at a point represents several things. It represents the derivative, of course, at that point. It represents the slope of the curve at that point. It represents the slope of the tangent line at that point. And then the final thing that the derivative at a particular point represents is it represents the instantaneous rate of change at that point. So that's what this lesson is about. We're going to be talking about this particular application of the derivative. Now, I call this the instantaneous rate of change, but oftentimes we omit the word instantaneous. So before we can really talk about this idea, we have to learn a little bit of vocabulary, and I highly recommend writing all of this down if you're not familiar with it. So the first term is the concept of position. So position is really talking about modeling how any object moves through a space. So usually we represent the idea of position by the letter S, although we can represent it also using F. So we have S or S of t or F of t, where t is talking about time. So you have the amount of time it takes for a particular object to move and how much it moves as it goes through an area. So from position, we have the idea of displacement. Now, displacement is how far an object moved in a period of time. The object started here, it moved over there, and this is how we measure that. So it's really a very basic idea. You have this delta S, that's how you say this, delta S. So it's F of t plus delta t minus F of t. So basically this idea here, this is talking about how much time has changed. And this would be the ending position, this entire thing here. This is ending position, this is starting position. So this triangle symbol, which we call delta, it really refers to any amount of time that has passed as an object goes from one point to the next, or really any amount of change. So here, this would be the actual change in distance, this would be the change in time. So that's what that triangle means. Okay, so the next term we have is what's known as instantaneous velocity or just velocity. Remember, we do drop the word instantaneous quite a bit when we refer to this. So this is this calculation. So check this out. Look good and hard at this definition. So this is just the derivative of the position function. And if you look at this, this is really the definition of the derivative, except we've just modified the definition. So instead of having an h, now we have a delta t. And because these are literally the same definition, this is why we say that the derivative can be so many things at once. Now, like I said, this definition is really just the derivative of the position function. This is the definition of a derivative. So we can use our derivative rules here. So our velocity function is just the first derivative of the position function, whichever way you want to represent the position function. Okay, so here's a question. What is the difference between velocity and speed? I'm talking about velocity here. So velocity indicates a direction while speed does not. So speed is literally just the idea of having your velocity without a direction. So how can we remove having a sign? Well, we can just take the absolute value. So speed is literally found by just taking the absolute value of your velocity function or by taking the absolute value of the first derivative of the position function. Okay, now acceleration. How do we define acceleration? Well, acceleration is actually just the first derivative of velocity, or it is the second derivative of position. So position, velocity, and acceleration, they are all actually related, and we kind of have a little bit of an intuitive sense of what they actually mean, which we'll discuss in a second. Now, just for funsies here, what comes after acceleration, right? So we've got the first derivative is velocity, the second derivative is acceleration. What comes next? It's what's known as jerk. Jerk is the third derivative of position. And then after that, we get snap, crackle, and pop. I can't make this stuff up, guys. That's what that's really called. Okay. Now, I think we all know intuitively what the idea of position, velocity, and acceleration are. But now I want to take a second to examine these concepts with motion. And hey, let's use my motorcycle to do this. So the first thing I want to think about here is constant speed or constant velocity, if we want to include a direction with this. So here is a video clip of me, my motorcycle, and my dog traveling at a constant speed. So what I want you to think about here is the velocity and the acceleration and the position function of this situation. So how do we model this? So what I want to do here is I want to come up with an actual realistic set of position, velocity, and acceleration functions. And I'm going to do that in conjunction with the graph. So I really want to understand kind of the intuition of how I know something moves versus the calculus. Okay, so let's pretend for fun here that I was traveling at the constant speed of 100 miles per hour. I was not, but we'll just have some fun here. Let's pretend my motorcycle can really cook. Okay, so thinking about what this particular function actually looks like, what kind of function is this? So what would the graph look like? This is just a line, right? The slope of it would be 100. So here I go ahead and I draw a positively sloped line. We'll say that this represents my 100t. So here's what motion looks like when you're moving at a constant speed from a just really algebra perspective, not even necessarily calculus. Now, let's think about the idea of velocity. If I wanted to figure out at what velocity was I actually moving at, and I know my position function, well, I could just take the derivative of this. So what is the derivative of 100t? It's just 100, right? So think about then, what does that particular graph look like if I wanted to graph out 100? That is just a horizontal line, right? So here it is. Here's my velocity function being modeled out. So I can see how it relates. Here's the position function, and then here's the first derivative. And I'm just kind of putting them all together so that we can visualize them. Okay, so now I want to think about acceleration. So forget about the calculus for a moment. Just if you're moving at a constant speed, are you accelerating the vehicle? You're not, right? There is no acceleration. So this actually makes sense from the calculus standpoint. If I take the derivative of 100, what is the derivative of 100? It's 0. That makes total sense because we just said we're not accelerating. So it's not that the acceleration does not exist. The acceleration just happens to equal 0. And we can actually model out 0, right? So here it is down here, and here's my acceleration. So taking what we know intuitively about moving at a constant speed, the calculus actually matches that particular situation. So now what I want to do is I want to compare that to the situation where we are riding downhill. Okay, so once again, here I am, once again with my sweet dog, and we're going down a hill in this case. Now, when I went down the hill, I had to have a little bit of speed just going into it just because as I was approaching the hill, so that's going to be a little bit different. And what I want to do once again is I want to model this situation, and I want to come up with just what would make sense as a position, velocity, and acceleration function. And in this instance, we're going to say that this line here, this is specifically the distance from the camera. Okay, so I actually think it's a little bit easier this time to think about the graph and then to back into what type of functions actually would make sense for this. So I started out at some distance, and then I started to come closer and closer to the camera. So at some point I was 0 feet away from the camera. And so my speed or my velocity would have been changing throughout, right? It wasn't going to be constant. It's actually, if you think about when you're at the top of a hill, you start to gain speed even if you're not hitting the accelerator. And let's say that I wasn't hitting an acceleration here, so I was just letting gravity do its work. This is what that position function would look like. Now, this to me looks like a downwards parabola. And like I said, I had a little bit of speed when I got this started. So I approached the hill and then I stopped hitting the acceleration. So let's say for a moment that maybe this would be an equation that could model this situation. Now, for our purposes, I'm going to be using meters just to model out this particular situation, just so we can play around with both units. And a lot of times when you work with these, you work with meters. So we'll just pretend for a second that this was all within meters. Okay, so now what I want to do is I want to think about what is the equation for my velocity. So I have to take the first derivative of this thing. Okay, so if I take that first derivative, here is my first derivative. So negative 9.8t plus 8.9. So this is kind of interesting, right? Because this is indicating a few different things. So first of all, this shows us that the velocity is constantly changing, right? As time goes on, the velocity is changing. Also, so as time goes on here, this appears to be getting more and more negative, right? So we're plugging something into this. So remember, velocity has to do with the idea of direction. And so while you might say, oh, well, speed can't be negative, sure, speed can't be negative, but we're not talking about speed, we're talking about velocity. So if the velocity in this situation is actually going negative, that's telling us about how the situation is changing and what direction we're actually going. So what this would indicate to me then is that as I come closer to the camera, that is a negative direction in velocity. And how do you know whether it's supposed to be positive or negative? That's honestly kind of arbitrary. So I could have flipped this situation around and totally changed the direction of all this. So you can kind of decide which way, or the problem will decide which way positive or negative is. And then you just kind of have to stay consistent with that. Okay, now what does this actually look like? What is the equation of this? This equation is really just a line, right? Now, I don't have this really drawn to scale it at all because it's kind of hard to draw with this graph here. But just so that we can visualize this for a moment, here we can see how velocity is changing. So velocity is changing at a constant amount, right? But it is constantly changing. That is very different from the situation that we had before. When velocity was actually truly constant, it was just this straight line and there was no change in it. Now we see that velocity is always changing. Okay, so now let's think about the acceleration. Now, like I said, I was not actually hitting the acceleration in this. I was just letting gravity do its thing. And what's interesting about this is if I take the first derivative, or if I take the derivative of this, I get just negative 9.8. So what this negative 9.8 represents, actually, this represents the constant for gravity in meters. So this is partially why I did this in meters. If you take a physics class, a lot of times they work with meters and gravity in meters, although they can also do it in feet. So this tells me then that gravity is kind of doing its thing, and it's just constantly acting on the bike. Now, if I wanted to graph that out, here is what that situation looks like. So now we've seen two situations, and in both situations, we actually have a constant acceleration. In this case, the constant acceleration is negative 9.8, so this is what gravity is doing to it. In the other situation, we had an acceleration that was constant, and it was 0, which was not no acceleration, as in non-existent acceleration, it was just 0 acceleration. So notice kind of the intuitive difference between these two situations. You know that you're accelerating in this situation. And so mathematically then, you would think that this should not end up as 0. That's what that would mean mathematically from a calculus standpoint. So these are just two examples of kind of how we can think of position, velocity, and acceleration, and how the calculus kind of relates to that. Now, I have one other situation I want to show you, which is the idea of dropping a ball. So I'm going to drop my dog's ball from a height of 6 feet, which is about 1.8 meters. And so here we go. And so as you can see, I had one take for this, so hopefully this works out. My dog was quite happy though, as you can see in the making of this particular video. Okay, so what is the situation that would actually model this? So the position of the ball can actually be modeled by this equation right here. And notice once again that we've got this negative 4.9 t squared. Once again, this is ultimately going to end up reflecting gravity, but we'll see that in a moment. So I started at 1.8 meters up, and so now a couple questions that can come up with this. When does the ball hit the ground? How do you figure that out? Is this even a calculus question? Well, this is talking about really position, right? And so really, I just need this equation to answer this. There's nothing about this that is indicating that we need anything other than the position function, because it's not asking us about rate, it's just asking us about time. So because of that, I can just set this equation equal to 0, and then I can solve. So I would solve, let's see, I'll use the white color here, not the green color. So I can go ahead and I can just subtract negative 1.8 from each side, and I'll make both sides positive. I'll just go ahead and divide each side by negative 1 there. So if I do that, then I can divide both sides by 4.9. So that comes out to we'll say that comes out to 0.37. And so then if I take the square root of that number, what I end up getting is that this equals somewhere around 0.61. So this shouldn't be too surprising. If you drop a ball, it's going to hit the ground really, really quickly, right? So this means that in about 0.61 seconds, the ball is going to hit the ground. So you would want to actually write that out and just explain that. So this was a non-calculus question. It's almost an algebra question. Okay, so another typical question that would be related to this. When the ball hits the ground, what was its velocity? Now this is a calculus question, right? Because we're actually talking about velocity, and we know that that is the first derivative of position. So now what I need to do is I need to take the first derivative here, and this is going to come out to negative 9.8t. So that's the first derivative. Now what the heck am I supposed to do with it? Well, it says when the ball hits the ground. We know when the ball hits the ground, right? That's exactly what we found in the last question. The ball hits the ground in 0.61 seconds. So at that moment, what is its velocity? What do I have to do? I just have to plug in then that information, that 0.61. So I just have to plug that in, and if I multiply that together, I get negative 5.978. Now again, it's not wrong here that this came out as something negative, because this is just indicating then the position. So the direction, sorry, not the position. So if this is negative, what that means is that the down direction is the negative direction, and up would be a positive velocity. Okay, so that answers that question. Now, another question here is, what is the acceleration of the ball at any time? Again, this is a calculus question. So what I need to do now is I need to just note what my first derivative was, which was negative 9.8t. And now I need to take the next derivative, which is just negative 9.8. So this, once again, should actually make sense. And this should be something that you do every time you try to work with some of these questions, is just ask yourself, can you understand, or does the answer make sense? So this is, once again, the constant for gravity. And if I just dropped the ball without trying to throw it or do anything else, I just let the ball fall to the ground, then gravity should be the only thing that's actually accelerating the ball. So it actually makes sense that this is that this is the answer that I got, right? And again, going down, so from an acceleration standpoint, going down is also going to be negative. So also works out there. So this is kind of the rationale that you want to have when you approach these, and you always want to think, does that answer make sense? So if I got 0 for my acceleration in this case, that wouldn't make sense, because I know that the ball is falling, and so anytime something is falling, you know that gravity has to be acting on it. So you always want to kind of take a moment just to think about, can you relate the number that you found, or the numbers or formula that you found, to a physical situation? Do those two things tie out together? And so that's kind of the overview of this lesson. I have other videos where I'll talk about more specific examples and kind of walk you through them, but just wanted to kind of cover the intuition behind this with you guys. Thanks for watching. I'll see you next time.